is 18.
Hit me.
Hit you? 26, you went over. You want to try again? Oh, hi there. We're just playing blackjack. Didn't hear you come in. Alright, a 10, a king is worth 10. Plus a 4, that's 14. Now the goal in blackjack is to get as close to 21 as you can. So 14, what would you like to do?
No, another one.
Hit me.
Hit me.
18, what would you like to do?
Hit me.
18, okay, 25, you went over 21. We're going to continue looking at probability. Now, the first question we're going to look at, this is something we've done already, is what's the probability of getting, let's say, 2 clubs in a row if I draw 2 cards out of a deck? Now, the way that we've been doing this is we've been saying, okay, draw 1 card, happen to be a spade there, put the card back in the deck, shuffle it, and draw a second card. And we looked at that and we found the probability of getting 2 clubs in a row would be a quarter times a quarter, because a quarter of the cards are clubs. And those are independent events. So the probability of me drawing a club, for example, the 10 of clubs, on the first draw, doesn't change the outcome of drawing a club on the second draw because I put the card back in. So the probability is still the same. So we can multiply those probabilities together. Now, of course, in most games you play using cards, you draw 2 cards like without putting one back in the deck. So what's the probability to get 2 clubs in a row if I draw a card and don't put it back in? Well, suppose my first card is a club. Well, now what's the probability the second card's a club? That probability is now changed. Since this card is a club, there are actually 1 less clubs in the deck, and the probability of getting a club on the second draw is no longer 1 out of 4. It's changed to something new. So we're going to look at that question right away. At the end of the lesson, I'm going to get you to calculate the probability that you deal someone a blackjack in the game of blackjack. And we'll talk about what that is too. Okay, so let's go. Let's take a look.
So today's lesson's on conditional probability. Now, conditional probability has to do with sort of the and probability. So the probability of events A and B occurring. We've talked about that already, and we've talked about the importance of A and B being independent events, so that the probability of A and B happening is the probability of A times the probability of B, provided they're independent events, meaning the outcome of event A does not affect the outcome of event B. So let's look at an example of that. The probability of drawing 2 clubs in a row from a well-shuffled deck of playing cards if the first card is replaced. Well, for event A, drawing the first club, there are 13 out of 52 clubs in a deck of cards, times the probability of getting a second club. Now, because you have shuffled the deck and put that club back in, the probability is still the same. Now, of course, those are a quarter times a quarter, which is 1/16. 1/16 or 6.25%. Okay, now that's not a very realistic example. Often when we're dealing cards, we don't put the first card back in the deck. However, and that's exactly what we're going to look at now, the first card is not replaced. Unfortunately, these are no longer independent events. For example, if I get my first card and it happens to be a club, the probability that I get another club actually goes down because there are less clubs in the deck because I have one in my hand. Or if I don't get a club, say I get a 5 of diamonds, then the probability of getting a club on the second draw goes up because now there's 1 less diamond in the deck and proportionally there's more clubs. It's not too difficult to figure out what this probability looks like. The probability of getting a club on the first draw is still 13 out of 52. Now, of those times, we still need a club on the second. There are 51 cards left in the deck, only 12 of them clubs. So we can still multiply those probabilities together, provided we've adjusted the second probability to represent the new probability given that there's 1 less club in the deck, or given that event A happened. Now, if I quickly figure that out, I actually get, this is the same, of course, as 1/4 times 12 over 51, which gives you, let's see, 12 over 204, which reduces to 3 out of 51, or about 5.9%. So you can see that that probability is slightly less. Now we do have a formula to do these types of probabilities where A and B are not independent events. So the probability of A and B happening is the probability of A times the probability of B given that A happened. So P of B given A is some other probability. In this example up here, I was able to calculate that. So the probability of A was a club on the first draw, and then I multiplied that by the probability of B given A. So the probability of drawing a club being 13 out of 52 times the probability of drawing a club on the second draw given that you've drawn a club on the first draw, which is 12 out of 51. So let's look at an example of how to use this formula. Okay, Lori is an avid golfer. She gives is what that should say. She gives herself a 70% chance of breaking par, scoring less than 72, if the weather is calm, but only a 15% chance of breaking par if it is a windy day. The weather forecast gives a 40% probability of high winds tomorrow. What is the probability is windy and she breaks par tomorrow? So let's talk about W, event W being wind. It's windy. And let's talk about event, I was going to say P for par. That might be a little bit confusing, though. So we'll say B for breaking par. Okay, breaking par is considered to be a very good score in golf. So what's the probability it's windy and she breaks par tomorrow? Well, these are not independent events. The probability that it's windy and she breaks par, well, she's less likely to break par if it's windy. So we calculate that by figuring out the probability it's windy and multiplying that by the probability that she breaks par given that it's windy. Well, the probability it's windy is 0.4. And the probability she breaks par given it's windy is that 15% we see right there, times 0.15. Multiplying those two together will give us our answer to this question, which is 0.06, or 6%. Okay, what's the probability she breaks par tomorrow? Well, all we need to do now is figure out the probability that she breaks par if it's not windy. Now, notational-wise, we can look at that as being the probability it's not windy and she breaks par, which, of course, the probability it's not windy times the probability she breaks par given it's not windy. Well, the probability it's not windy is 60%. And the probability that she breaks par if it's not windy is well, 70%. She gives herself a 70% chance of breaking par if the weather is calm. So 0.6 times 0.7 gives us 0.42. Sorry about that. 0.42. Okay, well, what's the probability she breaks par tomorrow? Well, we've looked at two separate cases, which are mutually exclusive. It's either windy or it's not windy. So one of those must happen in order for her to break par, which gives us 0.48, or 48% chance that she'll break par tomorrow. One thing we can do with this formula is we can rearrange it to get this right here. So if you take the formula that I've highlighted there and you divide both sides by P of A, the probability of event A happening, then you actually end up with a formula that gives you the probability of event B happening given A. So sometimes that might be what you want to know, the probability of one event happening given that the other one has happened. Now, I will say this, I don't think this formula is used as often as the other formula that we just used, but let's see an example. Now, this is an instructional example. It's kind of a silly way to do this question, but I'll show you what I mean. So Anna rolls a set of dice. She must roll a sum of 2 to win a board game, so she needs snake eyes, 2 ones. She accidentally rolls the dice off the table. Her friend Jim, for some strange reason, tells her that the sum of the dice is less than 7. which she's probably happy about because it was greater than 7, then she can't get a 2. Given this information, what is the probability that Anna has won the game? Well, we can actually use the formula up above. We can think of event B as being rolling a 2. And we can think of event A roll less than a 7. And then what we can do is we can use that formula. The probability of B given A is equal to the probability of A and B divided by the probability of A. So basically what we're saying here is, what's the probability Anna has won the game knowing that she rolled less than a 7? So the probability she rolled a 2 given that she rolled less than a 7. Well, what's the probability you rolled a 2 and you rolled a number less than 7? Well, remember back from our chart here, there's only one way to roll a 2. And that's if you roll a 1 and a 1. And there are 36 outcomes. There's a 1 out of 36 chance that you rolled a 2. Okay? And the thing is, if you rolled a 2, you must have rolled less than a 7. So we can still look at this as 1 out of 36. The probability of A and B, because they both happen at the same time when you roll that 2. What's the probability of event A happening that you rolled less than a 7? Well, let's just take a look. Rolling less than a 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 outcomes that are less than a 7. So the probability of rolling less than a 7 is 15 out of 36. Okay, well, 1 over 36 divided by 15 over 36. To figure that out, we multiply by the reciprocal. The 36's divide out, and we get a final answer of 1 out of 15. So we know that the probability that she rolled a 2, given that she rolled something less than 7, is now 1 out of 15. Now, it's kind of a silly example. I just want to show you that the formula does work. There's an easier way to obviously figure this out. If you just look at the table here, and we look at this, we know she rolled less than a 7. Okay, well, there are 15 outcomes I've highlighted that are less than a 7. So now there's 15 possible outcomes. Only one of them is a 2. So sure enough, she now knows that there's a 1 out of 15 chance she's rolling a 2 as opposed to 1 out of 36. So by all means, I'm just illustrating the equation here. This is not the best way to answer the question. You just use the table and you can come up with it like that. Okay, let's move on to the next one. In Vancouver, the probability that a day will be both cloudy and rainy is 25%. And suppose that 50% of all days are cloudy in Vancouver. Determine the probability it will rain given it is a cloudy day in the city. So let's talk about B. Event B is the rain outcome, and event A being the cloudy outcome. Now, clearly, these are not independent events. The idea that it's cloudy would affect whether or not it rains or not. Let's take a look at this formula again, too. The probability of B given A is the probability of A and B divided by the probability of A. In our example, the probability of A and B is 25%. And I'm getting that just from saying, okay, both cloudy and rainy. The probability of event A, it just being cloudy, is 50%, or 0.50. Okay, 0.25 divided by 0.5 gives you 0.5, or 50%. So basically, if it's a cloudy day, based on these numbers, there's a 50% chance that it will rain. Let's take a look at this example. Okay, a group of 100 sports car buyers. 40 bought alarm systems. 30 purchased bucket seats. And 20 purchased an alarm system and bucket seats. If a car buyer is chosen at random, bought an alarm system, what's also the probability they bought bucket seats? So let's look at event A as being the alarm system, that they bought an alarm system. And the probability, event B, sorry, is that they bought bucket seats. And the reason I've chosen to make the events that way is to use the formula exactly as we wrote it before. The probability of B given A is what I'm trying to find. We were told that this person bought an alarm system, so it's the probability they bought bucket seats, given that they purchased an alarm system. So that, of course, will be the probability of A and B divided by the probability of A. Now, if we read this question carefully, they're all out of 100, so they're easy to change into probabilities. The probability that they bought an alarm system and bucket seats is 20 out of 100, so 0.2, divided by the probability they bought an alarm system and 40 out of the 100, so 0.4. So again, this one actually turns out to be also 50%. Take a look at these statements, and if you're just following along, I'm going to recommend that you pause the video and that you see if you can figure out what must be true by seeing all this. I know they look a little bit difficult at first, but maybe just give this a try, see if you can get any of these. Okay, let's try them together. The first one says if the probability of A and B is equal to the probability of A times the probability of B. Well, that means that A and B are independent events. Sorry, let's just write that a little different. Let's say A and B must be independent. If you can multiply their probabilities together, then you know they're independent. How about if the probability of A and B is 0? Well, that means A and B can't happen at the same time, and we have a word for that. We say A and B are mutually exclusive. They can't happen at the same time. And sometimes we might use that fact to say the probability of A or B happening is just the probability of A plus the probability of B. The third one here says the probability of B given A is just the probability of B. So that means that the probability of B given this event A has happened is just the regular probability of B. Well, that means A and B are independent. It's like this. It's basically saying, look, B doesn't care if event A happened or not. Its probability doesn't change, so A and B are independent. And finally, the probability of B given A is 0. So that means event A happened, and the probability of event B happening is now 0. That means A and B are mutually exclusive. They can't happen at the same time. Okay, well that's it for this lesson. Please try some of the practice questions, and I look forward to doing some more probability with you later on in the near future. Bye for now.